We're in Rosen, Discrete Mathematics and its Applications, section 12.3 on logic gates. We're looking at an example of how we would use Boolean logic to create an adder for binary mathematics. All right, so the first thing we're going to do is to build a half adder that adds the 2 bits, but doesn't need to take into account a carry bit from a previous addition because we always start on the right-hand side of addition without a carry digit. And here's a Boolean table for how the sum digit, the thing we write down below the when we're doing the adding, and then the carry digit would be. So if we have a 1 and a 1, we're going to write down a 0 and carry a 1. If we have a 1 and a 0 in x and y, we're going to write down a 1 and carry a 0. And if we have a 0 and a 0 in x and y, we're going to write down a 0 and carry a 0. So this is an example of a multiple output circuit because I've got two output columns. But that's okay, a logic gate can do that. And then what we're going to do is create sum of products expressions for the sum digit and the carry digit. And here they are. The sum digit has 2 minterms, x times y complement plus x complement times y. And the carry digit only has 1 minterm, it's x times y. All right, so with this fairly simple minterm or sum of products for S and C, the sum digit and the carry digit, we're going to create a circuit that implements this half adder, and here it is. This upper portion represents the sum digit, and this lower portion represents the carry digit. And you can see that this will implement the right-hand portion of adding binary numbers. It gives us S0 and the carry digit C0. Okay. Well, now we're going to take this function, or this logic circuit, and combine them together in order to do a full adder. That is, that takes into account when we have x1 and y1, we'll use a half adder to add these two, and then we'll use another half adder to add in the carry digit. So that's what we show on the next chart. We also have the table for that, for the full adder on the right as well. Now a full adder is going to have 3 inputs. It's going to have x and y and the carry digit. And just note that the indices are not correct. I get this table from the book. They should be, the carry digit should have the index from the column it came from. Okay, so what we're doing here is we basically can see the 2 half adders that we have here, and we're using 1 half adder to add x1 and y1, or xi and yi, to get an interim sum and an interim carry. And then the actual sum digit will be the sum of the interim sum and the carry digit. That's this right here, to give me the write down digit for the ith column. And the actual carry digit will be the sum of the interim carry digit from the first half adder and the interim carry digit from the second half adder added together. So these 2 half adders will implement the full adder, and we can see that we get these functions for our sum digit, and the carry digit is the sum of ci prime plus ci double prime. All right, so now the other thing we could do is look at the multiple outputs here. We have S as an output and C sub I as an output, not sub I plus 1. And use sum of products to write down these expressions. So what we're going to do is compare our output to the sum of products expansions from this table. So on the next slide, we have the write down digit from before and the carry digit from before. And then we'll just start substituting for each of these values. And we see that we get the sum of products expansion from the table, so that our half adder is shown to give us our half adders combined is shown to give us the performance of the two adders. Now that we have a half adder and the ability to create a full adder, then we can create an adder for any size of binary number, where the top digit and the bottom digit on the right are added using a half adder. In the next column, they'll be added using a full adder along with a carry digit. And then the next column, you added using a full adder and the carry digit and so forth to get our final sum. And we can make this as long as we need. And that's taking Boolean logic circuits to actually do binary mathematics.